Hello everyone, and welcome to a couple of examples of using the law of conservation of momentum to look at collisions quantitatively. That means we're going to use equations here rather than the crutch of the bar graphs that we used on the last worksheet. So, we're going to do two examples today, the same two we did the other day, but again, we're going to use equations. So here's example number one. You might remember it. Looks something like this. You might remember that the boy moved away faster because the man has more mass, the boy has less mass. But if we call our system the man and the boy, since it's a smooth ice surface, so there's no friction, the only horizontal forces are the forces between the boy and the man. Therefore, the system is isolated and closed, no mass changes, and therefore momentum is conserved. How do we write that as an equation? Very simply. Initial momentum is simply equal to the final momentum. The total initial is equal to the total final. Now, rather than using bar graphs to do this and to kind of keep track of all of our objects and all of our momenta, we are going to just write it out as an equation. Initially, the man isn't moving, and since he's not moving, he has no momentum. Remember, to have momentum, you must have both a mass and a velocity. However, afterwards, both the man and the boy are moving, and therefore both have momentum. So, the initial momentum of the system is 0, but the final momentum is the vector sum of the momenta of the man and the boy. And notice there, it's a vector equation. It's not scalars. We are doing vector algebra, and therefore eventually we're going to have to deal with directions. This is not energy. Energy is a little simpler in that sense, that energy is just a scalar, an amount of ability to produce change. Momentum is mass times velocity. It's a vector quantity. So we're trying to find the final velocity of the boy, which will be locked inside of the equation for the momentum of the boy. Notice here I'm using subscripts, so man and boy, so we can tell which is which. So if we solve for the final momentum of the boy, we get that's equal to the negative of the final momentum of the man, and each momentum is simply a mass times a velocity. If you're sloppy here and you just write mv and mv, it looks like everything cancels out, which of course can't be true. So use subscripts. Use an A and a B. Use a 1 and a 2. Use something descriptive, B for boy, M for man. But use something as a subscript so that you can tell which object you're talking about in which case. Divide by the mass of the boy to solve for the final velocity of the boy, and plug in our numbers. But we have to be a little careful here. Think back to the previous screen. The man was moving in which direction? To the left. And therefore his velocity is negative. This is a vector. So here the two negatives cancel out, and we get a positive velocity for the boy. So notice the boy and the man go in opposite directions. Notice here too, the boy has half the mass, and so he ends up with twice the velocity because there is no initial momentum. So the momentums have to be equal and opposite. It's explosions, right? We found that out in our explosion lab, that you always get that nice ratio thing you can do with those. So half the mass is twice the velocity. So hopefully you can see here how we wrote this out with the equations. I mean, personally, of course, I like equations. You might just do this with numbers instead of writing it out symbolically, but it is not a bad way to work these problems. So here is example number 2. The 10-gram bullet is moving horizontally at 400 meters per second, embeds itself into a much more massive 0.39 kilogram block of wood that is initially at rest on the frictionless table. And I want to know what's the final velocity of the bullet and the block after the collision. This obviously is a highly inelastic collision because the bullet's going to embed itself in the block, dissipating lots of energy. Lots of energy will be stored as thermal and deformation of the bullet and the block, and probably a nice loud sound. And so all of those things will dissipate energy. However, if we include the bullet and the block in the collision, it is still isolated and closed horizontally, and therefore momentum is still conserved, even if kinetic energy isn't. So, if momentum is conserved, that means the initial momentum is equal to the final momentum. Now we just have to list out all of the initial and final momenta. Initially, again, in order to have a momentum, you must have a mass and be moving. and the only thing that's moving is the bullet. So initially, we only have a momentum of the bullet. Finally, both objects are moving. But they're moving as one thing here because the bullet's embedded in the block. So we could write this as two separate momentums. The final momentum of the bullet plus the final momentum of the block. But I would prefer to do this as the final momentum of the combo. Since it's moving together anyway, it's moving like one big object, let's just write it out that way. You do have to be careful though at this step, because now each momentum is a mass times a velocity, but the mass finally is the combo mass, because we're talking about both objects moving together. So make sure you are careful about your masses. Notice here how the symbols are being used to show us the bullet versus the wood. Right, so I'm calling it bullet and wood here. And that will help us when we plug in numbers. Solve for the final velocity. Plug in your numbers. Notice they all have to be in either kilograms or grams. It really doesn't matter which way. As long as they're all in the same mass units, it's going to cancel anyway. And we get a nice 10 meters per second. Notice it's going much slower because there's much more moving mass. The MOP guy is going to actually ask you some proportional thinking things with these, but this is how you write it out. Hopefully you see here how we can start out with the law of conservation of momentum, assuming our system includes all of the objects. And then we can simply write out the initial momentum on one side, the final momentum on the other side, and solve for whatever we don't know. For example, this problem is often done the other way. We would use some sort of motion detector to measure the final velocity of the block and the bullet, and then we could work backwards and figure out the muzzle velocity of the gun. That's one way, a ballistics way of figuring out the muzzle velocity of a gun without using some sort of radar detector to do it, because it's so small, it's sometimes hard to do. So this is kind of the old way of figuring it out. So I hope you enjoyed these couple of examples of using our wonderful equations to solve problems of conservation of momentum quantitatively.